last lecture I considered dynamics in the sense that I looked at the time dependent Schrodinger equation, and we will apply it to certain systems. We will continue to apply it to certain systems today. So, I had called this lecture also, title it Applications. Would be discussing the dynamics of various initial states in a box, various initial states of a particle in a box. Also look at a certain superposition of harmonic oscillator energy eigenstates and the way they behave under the quadratic potential, the manner in which they change with time. I also said in the last lecture that we will look at an alternative formalism of quantum mechanics where the operators evolve in time and the state vectors do not, the Heisenberg picture as it is called. I will get to that towards the end of this lecture perhaps, after working out these applications that I was talking about, the dynamics of a particle in a box, different initial states given, and also the dynamics of the harmonic oscillator states. So, the first thing I will consider is a box, a one-dimensional box. Size is L, 0 to L, and the eigenstates of this one-dimensional box, the energy eigenstates are given by phi n of x and since we have already done this problem, you know what the phi n's are. The normalized energy eigenstates are given by root of 2 by L sin n pi x by L, where n takes values 1, 2, 3 and so on. The energy E n itself is known to us, n squared h cross squared pi squared by 2m L squared. So, these are the energy eigenvalues, and since these are eigenstates, the phi n of x, the manner in which they evolve with time is very simple. Phi n goes to some psi n of x t with time, which is e to the minus I E n t by h cross phi n of x. These are stationary states and this is the time evolution. Of course, we remember that h is not a function of time. It is a conservative system. The energy does not change in time. Hamiltonian is not a function of time. So, now we ask the question, what about an arbitrary state psi of x t? How do I write it in terms of the basis states? Well, psi of x t can always be written as summation over n c sub n psi n of x t. So, at any instant of time, this is a linear superposition of the eigenstates, the evolved eigenstates of the Hamiltonian, and it is clear therefore that at time t equals 0, psi of x is simply C n psi n of x 0, which is phi n of x. So, now let us start with arbitrary initial states psi of x comma 0 and see how exactly it evolves in time. In other words, one wants to find out what the C n's are. So, the simplest example that we can think of is this: psi of x 0 is root of 2 by L for L by 4 less than x less than 3 L by 4. other words, that is x, and this is psi of x, takes value root of 2 by L, just from L by 4 to 3L by 4. So, it is a constant independent of x, and this is psi of x. So, if I want to find out, the problem is to find out psi of x comma t. The manner in which I find out Cn, of course, is to say that Cn, Cm in general, is integral psi of x 0 phi m of x dx from 0 to L. And once I know the Cm's, I plug it in here and I get psi of xt, because I know psi sub n of xt from that equation. So, let us work that out and see what we get. So, in this example, Cm is root of 2 by L. Since since psi of x 0 vanishes everywhere except from L by 4 to 3L by 4, this integral itself needs to be done only within those limits. That is the root of 2 by L again, sine m pi x by L dx, which is 2 by L minus cos m pi x by L by m pi by L. So, I can always put a plus sign and go from 3L by 4 to L by 4. So, that is 2 by m pi cos of m pi by 4 minus cos 3 m pi by 4, and this is what I have for Cm. So, certain things are obvious. Remember that m takes values 1 upwards, so there is no problem here, but for all even m's this vanishes and it only survives for odd values of m. So, I have Cm equals 0 for even values of m, and Cm not equal to 0 for odd values. Of course, m takes only integer values, so I can substitute now and get psi of xt as summation over m 2 by m pi. So, Cm is known, you can substitute 2 by m pi cos m pi by 4 minus cos 3 m pi by 4 e to the minus I emt by h cross phi m of x, which is known, phi m of x is root of 2 by L sine m pi x by L, and therefore, you find psi of xt. So, for a given initial state, an arbitrary initial state, we now know what the temporal development is like and how it evolves at a subsequent time. Now, of course, at some instant of time, later time, this could become one of the eigenstates themselves. It could continue to be a linear superposition of the eigenstates. Many things can happen. So, but this is an example where the initial state was an x independent object. So, let us go to the next level of complication. I am going to use a different psi of x comma 0. So, let us say that this is some positive constant lambda delta of x minus L by 2. So, that is the delta function there, and that tells us therefore that the state is sharply localized at x equals L by 2. So, somewhere in the middle of the box and nowhere else, there is no spread, and there is a weight here, there is a lambda. So, what happens in this case? So, once more we can find out Cm, and that is root of 2 by L lambda integral 0 to L delta x minus L by 2 sine m pi x by L dx. Do you see what this is? This is simply sine m pi by 2, because I just replace x by L by 2. So, one thing is clear, if m is even, the Cm's vanish as before, and if m is odd, the Cm's survive. So, what does it mean for psi of xt? Psi of xt is summation over n Cn, these are constants, sine n pi by 2, and that is as far as Cn is concerned, psi n of xt. Where psi n of xt is simply e to the minus I Ent by h cross phi n. So, this object is root of 2 by L lambda summation over n sine n pi by 2 e to the minus I Ent by h cross phi n of x. But you can already see what this is going to be. Sine n pi by 2 is minus 1 to the n. And this is what I have, and if I also substitute for phi n of x, I pick up a 2 by L here times lambda sine n pi x by L only for L odd. So, let us say this is summation over n 2n plus 1 pi x by L, and this n is again really an odd number 2n plus 1, where n runs from 0 to infinity. I ask the question, what is the probability that psi of x comma t is in some eigenstate phi n? In other words, I ask for this. What is the probability that this wave function happens to be in an energy eigenstate? Because you can see there is going to be a mod square that comes up for the probability, and that is essentially going to involve this object mod square. In fact, these Cn's, of course, they are non-zero only for odd n's, odd values of n. It is not finite. It is not finite for a very good reason. We did not start with a normalized state psi of x 0. If you want to normalize this, you do integral psi star of x psi of x dx is 1, and then the square of the delta function is involved, and that is not defined. Therefore, if you take something like a delta function for the initial state, you see that you can't have a consistent probabilistic interpretation, because mod Cn squared is not even finite. And the reason for the problem was here. So, one way of handling this is to consider an initial state which is not so sharply peaked like a delta function, something which is tempered a little bit, and then perhaps we can go to the limit of the delta function. So, let us look at a different kind of initial state psi which is somewhat tempered. So, I give you this initial state, some constant A x for 0 to L by 2 and A times L minus x for L by 2 to L. So, the whole idea was to take a function which is normalizable, in other words which belongs to the class of square integrable functions. So, which means we have to fix A. So, integral psi star of x, here it is real, dx from 0 to L should be 1, and that means 0 to L by 2 A squared x squared dx plus A squared integral L by 2 to L of L minus x the whole square dx is 1. That should fix A for us. So, this tells us that A squared by 3 times L cubed from 0 to L by 2, x cubed from 0 to L by 2 plus this integral should be 1, and it is clear what happens. A squared by 3 can be pulled out, and I have L cubed by 8 plus L cubed by 8. So, that is L cubed by 4 is 1. In other words, A squared is 12 by L cubed, and therefore, A is root of 12 by L cubed. This is therefore a good wave function, belongs to the class of square integrable functions, and I have fixed A so that integral psi star psi dx is 1. So, with this function, let us see how the initial state looks. So, if I plot psi star psi of x versus x, that is L by 2. So, here there is a linear rise up to L by 2. So, it looks like a tent, and this is psi of x versus x. So, it is not the constant that we considered in our first example, it is not the delta function which we considered in the second example, something like this. So, how does the probability density look? So, if I plotted psi star psi, just write this as modulus of psi squared or psi squared, it is clear what happens. Of course, it is 0 here and 0 there, and the maximum probability is at L by 2. Something like that, symmetric of course, like a cusp. So, this is a good function to consider, and now in this case let us find out the Cns, and therefore, psi of x comma t, the subsequent evolution. So, Cn is integral psi of x comma 0 phi n of x dx from 0 to L. So, from 0 to L by 2 it is A x root of 2 by L sin n pi x by L dx plus root of 2 by L a integral L by 2 to L L minus x sin n pi x by L dx. So, this is the object that I have to find. This gives me C n, and I substitute it back and get psi of x t because everything else is known. Psi n of x t is known and C n's are these. Now, if you did that, you get this to be psi of x t. Apart from a constant 8 root 3 by pi squared root L, there is a contribution minus 1 to the k by 2 k plus 1 the whole squared sin n pi x by L. Note that contribution comes only when n is odd, and that is why I have written instead of n I have called it k, and therefore I have written 2 k plus 1 pi x by L. This integral out here vanishes, the C n's vanish for n even, and there is a contribution only for n odd, and that is why there is a 2 k plus 1 pi x by L there. And then of course I have to put in an e to the minus I e n t by h cross. So, remember that E n in this problem is n squared pi squared h cross squared by 2m L squared, and therefore I have exponential of minus I e t by h cross, and that is why there is just one h cross out there. This is what you get for psi of x t. Leave it to you as an exercise. Once you do this, you can ask, what is the probability that psi of x t is one of the phi n's? Now, if you looked at that, essentially you will have to look at the C n's. Look at this factor here. The probability, of course, this exponential is not going to make a contribution. The C n's, it is mod C n squared which is going to give us a contribution, and that object is independent of time. Therefore, the probability density for psi of x t to be one of the energy eigenstates is independent of time. That is what we get as a result for this problem. So, these are the various cases that you can consider as examples for initial states in a square, in a particle in a box. And each of the problems that I have considered demonstrates different aspects of the problems that you can face when you work with a particle in a box. And in general, now you have a machinery by which you can get hold of psi of x t. Given an initial state psi of x comma 0, which is not an energy eigenstate, in many physical problems one is compelled to find the subsequent evolution. For instance, when a laser interacts with an atom, when light interacts with an atom, the light perturbs the atom, and therefore both the initial state of the light and the initial state of the atom change in time. And what you will have is a subsequent evolved state psi of x t, which could show entanglement. Those will be problems that I will consider when I do perturbation theory in the next few lectures. But as such, now that we have started doing dynamics, in this case, because we only have an initial state and see how it evolves under a Hamiltonian, these are one dimensional problems and things are relatively simple. But for instance, when you consider interaction of light with atom, you have two different states. You have the state of the atom and the state of the light to consider, and initially they could be factored product states. For instance, initially the state of the light could be a coherent state. So, if I refer to the light as subsystem A of the entire system, A could well be the coherent state, and it is a factored product of the atom state, maybe the excited state of the atom, maybe the ground state of the atom, and I call the atomic system B. Now, this is a factored product, but depending upon the kind of interaction between the light and the atom, subsequent evolution may not lead to such a factored product, and while this is psi of x0, psi of xt could be an entangled state. In other words, you may not be, and in general you will not be able to write psi of xt as a factored product of the atom state and the laser light state, the light state, so the radiation field state. So, these are the kind of problems that we will consider subsequently, but to begin with, since we know the particle in a box problem, it is good to look at this, and since we know the harmonic oscillator problem, it is good to look at the coherent state of the oscillator and see how it evolves in time. So, therefore, bearing this application in mind, which I will look at in subsequent lectures, I now wish to do another example, not the particle in the box, but the simple harmonic oscillator. Consider the ground state psi 0 of x. You will recall that the Hamiltonian was p squared by 2m plus half m omega squared x squared. You will also recall that the ground state of the oscillator in the position representation was a Gaussian, and in fact psi 0 of x, apart from a normalization n, it had e to the minus rho squared by 2. I defined a dimensionless variable rho is alpha x, where alpha had dimensions of inverse length times hn of rho, and n of course took value 0, 1, 2 and so on. So, this was a normalization. This came by looking at what happens when psi goes to infinity, the asymptotic x goes to infinity or rho goes to infinity, the asymptotic form, and the hn of rhos are the Hermite polynomials. This normalization n itself is root of alpha by root pi 2 to the n factorial, and hn of rho is the Hermite polynomial. It is e to the rho squared minus 1 to the n dn by d rho to the n e to the minus rho squared. So, this is what you will substitute here to get the ground state of the oscillator. Now, with this ground state of the oscillator, you know that you can construct a coherent state which is got from the ground state by using the displacement operator. The coherent state itself is a minimum uncertainty state, it is another Gaussian, and I will refer to that as state mu in abstract notation, mu being a complex number. Of course, I could do this, and this gives me psi of x. My initial state in this problem is this object, which is e to the minus mu squared by 2 summation n equals 0 to infinity mu to the n by root of n factorial psi n of x, where psi n of x is the energy eigenstate. Maybe I should call it phi n of x, because all the while I have been referring to the energy eigenstate as phi of x. So, call this phi 0 of x. This too is a minimum uncertainty state as we have seen, and if I write mu as some lambda e to the I theta, because it is a complex number in general, psi of x0 in this problem is e to the minus lambda squared by 2 summation n, which goes all the way to infinity, lambda e to the I theta to the n by root n factorial times phi n of x. This is phi n of x, this is the nth eigenstate phi n of x. This is a normalization which I have put on here. So I can well substitute for all these objects and I will get psi of x0. Question is, what is psi of xt? It is clear that the phi n of x are stationary states of the system. Therefore, phi n of xt is e to the minus I E n t by h cross phi n of x, and E sub n itself is n plus half h cross omega. So all the information is there and now we merely need to find out what exactly is the subsequent evolved state psi of xt, or the initial state which was the coherent state. How does that look at the end of time t? Now in general several things can happen. A coherent state, in other words in this case a minimum uncertainty state, a Gaussian, need not continue to be a Gaussian in general. Therefore it need not be a minimum uncertainty state for all times, and it could do anything. It could simply be a very complicated looking object as a function of space and time. In fact, at every instant of time it could put out tendrils. The wave function can be very complicated, but of course with the condition that it can be expanded in terms of the basis states of the harmonic oscillator Hilbert space. In other words, it can be expanded in terms of the energy eigenstates at all times. But given that it need not have the Gaussian shape and it can change arbitrarily, whatever I have said is true for a generic Hamiltonian. The precise question that we are asking is, how does it look, how does it evolve under the harmonic oscillator Hamiltonian? So that is the problem that we would like to look at now. So let us find out psi of xt in this problem, substitute for everything. So psi of xt is simply going to be equal to e to the minus I E n t by h cross. Of course, let us start with the fact that it is a coherent state. So e to the minus lambda squared by 2 summation n equals 0 to infinity lambda e to the I theta to the n by root n factorial phi n of x t, which is e to the minus I n plus half omega t. So I have taken care of the time evolution of the stationary state and I substitute for phi n of x. It has a normalization root of alpha by root pi 2 to the power of n factorial, okay, and then e to the minus rho squared by 2 h n of rho and h n of rho was minus 1 to the n e to the rho squared d by d rho to the n dn d rho to the n e to the minus rho squared. So this is the object that I have. So there are certain things that I can pull out here already. First of all, I can pull out a root alpha by root pi, and then e to the minus rho squared plus lambda squared by 2. This together gives me an e to the plus rho squared, and therefore it is rho squared minus lambda squared by 2. So I have taken care of this object and this and this. I guess I have to put everything else inside the summation. So I have summation n equals 0 to infinity lambda e to the I theta, and then I have an e to the minus I omega t. So e to the minus I omega t, the whole to the n, but then I also have a root 2 here. So perhaps I can write a lambda by root 2, the whole to the n. There is an n factorial because there is a root of n factorial there and a root of n factorial out there, and therefore that gives me this object. But I also have an e to the minus I omega t by 2, which I can pull outside. Minus 1 to the n, therefore I will put a minus sign here, and then I have dn by d rho to the n e to the minus rho, dn by d rho n e to the minus rho squared of e to the minus rho squared. So this is what I have. Which is precisely the expression that I have written out here for you. If you look at it, root of alpha by root pi came from the normalization for the eigenstate, energy eigenstate. E to the rho squared minus lambda squared by 2 e to the minus I omega t by 2 is what I have pulled out here. Then there is a summation over n with precisely the factors that I have put down there. But you compare this psi of xt, this expression for psi of xt, with the Taylor expansion for f of rho minus eta. You can write a Taylor series for any function of rho minus eta in this fashion. So if you compare with whatever you have here, there is a summation over n minus eta to the n by n factorial dn by d rho n e to the minus rho squared. So this f of rho is e to the minus rho squared, and the eta is out here. So I have identified eta in the Taylor expansion as lambda e to the minus I omega t minus theta by root 2. And therefore what I have is psi of xt, which can be now written as root of alpha by root pi, these things do not change, e to the minus I omega t by 2, e to the rho squared minus lambda squared. But I can see that this compares with my Taylor series, and therefore I can write this as e to the minus, this is my function of rho, where eta itself is lambda e to the I theta e to the minus I omega t by root 2. So that is what I have. By itself this is not particularly instructive. Suppose I find psi star psi. Suppose I find the manner in which the probability density varies. Of course, this would cancel out. I have an alpha by pi. Remember that the eta has a time dependence in it, and if you put that all in, I leave it to you as an exercise to show this. This is the exercise. Modulus of psi the whole square is alpha by root pi exponential of this object. The time dependence came not from this, because in psi star psi this term would cancel out, but eta has a time dependence, and from there the time dependence turns out to be cosine omega t minus theta. So it is an exponential of minus of this object the whole squared. Remember that alpha has dimensions 1 by length, it is root of m omega by h cross. So, this is what I have. So, what does it tell me? First of all, the initial state was a Gaussian function of x. Psi of x 0, if you put things in, was a Gaussian function. It was e to the minus alpha squared x squared by 2. So, this was a Gaussian function of x. At any instant of time, it continues to be a Gaussian function of x. The motion itself is simple harmonic. So, what happens to the ground state of the oscillator or a coherent state? I have taken a coherent state, a Gaussian. As a function of x, what happens to it? First of all, at time t equals 0, it starts off as a Gaussian, and then it simply executes simple harmonic motion without changing its Gaussian form. So, in the harmonic oscillator potential, a coherent state continues to be coherent, and in a very popular sense of the term, you can understand why this is called a coherent state. It does not change its form, it does not change its height, it does not change its width, it simply continues to oscillate in time, executing simple harmonic motion. In that sense, it is like a classical oscillator. And the coherent state, again in that sense, is the closest you can get among the quantum states and their superpositions to something very classical. It is a minimum uncertainty state, and in the oscillator potential, it simply moves back and forth, executing simple harmonic oscillation. Of course, the amplitude of the oscillation would depend upon lambda. But unlike the case of other more complicated potentials, which I would talk about in my subsequent lectures, in the harmonic oscillator potential, the coherent state continues to be a coherent state, merely executing simple harmonic motion. So, having looked at these examples, let me finally look at an alternative picture, the Heisenberg picture which I was mentioning, where operators evolve in time given by the Heisenberg equation of motion and the state vectors do not. So, as a prelude, I have already indicated to you what happens in the Schrodinger picture. There is the time dependent Schrodinger equation. Let me start by saying that H is not a function of time. The Hamiltonian is not a function of time. Then psi of t is e to the minus I h t by h cross psi of 0, and I call e to the minus I h t by h cross as u, since it is a unitary operator. A itself, any operator A, can have explicit time dependence. I gave an example, could be A cos omega t or P cos omega t. All this is possible, but P is a linear momentum. Now, having said that, suppose I consider an alternative picture where I do the following. I say that in the Heisenberg picture, which is the other picture that I will consider, psi h at any instant of time is u inverse psi Schrodinger, which is what I was considering here. So, let us put psi s of 0, psi s of t to show that we are in the Schrodinger picture. So, I go from the Schrodinger picture wave function at an instant of time to the Heisenberg picture wave function at the same instant of time by applying u inverse, and remember u inverse is e to the I h t by h cross. So, I have e to the I h t by h cross. Psi s of t is e to the minus I h t by h cross psi s of 0, and therefore, the state vector in the Heisenberg picture does not evolve in time. You take the initial state in the Schrodinger picture, that is going to be the Heisenberg picture state vector for all times. So, how does the dynamics come in? The dynamics comes in through the operator evolution. Expectation values at any time will have to be the same whether you are in the Schrodinger picture or in the Heisenberg picture, because expectation values are measurables and the picture you choose to work with is often just a matter of convenience. And therefore, I could have well done this by starting with psi s of 0 u inverse a u psi s of 0. Remember that u psi s of 0 is psi s of t, and therefore u inverse psi s of 0 on this side gives me the bra psi s of t. So, if I now say that u inverse a u is the operator in the Heisenberg picture, then it is evident that while psi h of t is simply psi s of 0, the operator a h is u inverse a Schrodinger u, and then it is clear that the expectation values at any time in both pictures are the same, and that is what we want, because the measurables should not depend upon which picture we use for convenience of calculation. So, what does that mean? By way of an equation of motion for the operator, I have a h of t is e to the minus u inverse, so e to the I h t by h cross. Oh, remember, by this token, what is the Hamiltonian in the Heisenberg picture? It is e to the I Hamiltonian in the Schrodinger picture. This is u inverse h s u, and since things commute with each other, that is just h s. So, and the Hamiltonian therefore is not a function of time and continues to be the same, be it the Schrodinger picture or the Heisenberg picture. But now let us look at any operator a h of t, that is e to the I h t by h cross. Will not put a suffix s or h here, because we have said the Hamiltonians are the same through this transformation, a s e to the minus I h t by h cross. So, let us get an evolution equation for a h. So, dAh of t by dt, this can only have explicit time dependence if at all. So, in the differentiation I have an I h by h cross e to the I h t by h cross a is e to the minus I h t, which is a h, plus e to the I h t by h cross delta a s by delta t e to the minus I h t by h cross. This differentiation is non-zero, this value is non-zero if a s has explicit time dependence. Then there is a third term which is minus I by h cross e to the I h t by h cross a s h e to the minus I h t by h cross. So, therefore, this is I by h cross h a h minus, notice that this object commutes with h, the same thing out there, and therefore, that term can be written as minus a h h. So, I have a commutator plus this quantity, I am going to refer to it, I am going to refer to this quantity as delta A by delta T in the Heisenberg picture. This is a notation that I use. By this I mean differentiate with respect to time just the explicit time dependence in the Schrodinger picture, sandwich it between u inverse and you get this object in the Heisenberg picture. This is my definition. So, what does that imply for the equation of motion? I have the following. dAh of t by dt, which is the total time dependence, is minus I by h cross commutator of ah with h plus delta A by delta t in the Heisenberg picture. In tune with the Schrodinger equation, let us work with IH cross dAh by dt. This object is simply the commutator of AH with H plus IH cross delta A by delta t in the Heisenberg picture. Now, this is called the Heisenberg equation of motion. Like you have the Schrodinger equation in the Schrodinger picture, which tells you how the state vector evolves in time, or the wave function evolves in time. In the Heisenberg picture, there is an evolution of the operator with time. The total evolution has two parts, one given by the commutator of the concerned operator with the Hamiltonian, and the other comes through a possible explicit time dependence. Compare this with what you have in classical physics. In classical physics, any dynamical variable A, if you want to find out its evolution, temporal evolution, A classical, dA classical by dt is the Poisson bracket with the classical Hamiltonian plus delta A classical by delta t. Compare these two equations. The Heisenberg picture seems to be closer to classical physics because the equations are very similar, and all said and done, it's the dynamical variables in classical physics that are replaced by operators in quantum physics. How do I make the connection? Well, the Poisson bracket here is simply the commutator bracket by IH cross. So, let us write that down. The Poisson bracket of A classical with H classical is just the commutator bracket by IH cross in the limit H cross going to 0, because that is quantum physics going to classical physics. Take a simple example. Take for instance the commutator bracket between x and px, IH cross, and what is the classical x classical with p classical, px classical Poisson bracket, that is 1. So, what is the commutator xpx by IH cross? In the limit, of course, H cross going to 0, which is okay in this case, the H cross cancels out the numerator and denominator. This goes to the Poisson bracket. So, that is one of the good things about the Heisenberg picture. It looks very similar. The evolution equation is for the operator, which is simply the dynamical variable with a hat on top of it, and the evolution equation looks very similar. The evolution equation, the Heisenberg equation, looks very similar to the evolution equation for the dynamical variable in classical physics. So, now let me do an example applying the Heisenberg equation of motion. So, I consider an operator in the Heisenberg picture AH, which is minus p cos omega t minus m omega x sin omega t. Now, pH is simply the momentum operator. Let me put down the Hamiltonian. The Hamiltonian is the Hamiltonian for the simple harmonic oscillator, which is pH squared by 2m plus half m omega squared x h squared. So, you see, I have got the momentum operator here and of course, the position operator, both written in the Heisenberg picture. This was an explicit dependence on time Please remember that the Heisenberg picture operators are unitarily transformed versions of the Schrödinger picture operators. Therefore, this is certainly true. The Lie algebra holds in whichever picture you are in. I did not write H sub H because, as I have already told you, the Schrödinger picture Hamiltonian is the same as the Heisenberg picture Hamiltonian. So now let us look at the equation of motion. IH cross dAh by dt is a commutator of A with H plus IH cross delta A by delta t. This is the explicit time dependence. In this problem, let us calculate these two terms. So what is the commutator of A with H? It is minus cos omega t by 2 m omega squared commutator of P with x squared, because this anyway commutes with itself. There is another term minus m omega by 2 m sin omega t commutator of x with P squared. But this quantity is minus IH cross and this is plus IH cross. This is plus 2 IH cross PH and that is minus 2 IH cross XH. I have just used the ABC rule for commutators. So this object is simply IH cross m omega squared XH cos omega t, that is the first term, and the second is minus IH cross m omega PH sin omega t. So this is the commutator. Now let us look at the explicit time dependence. Delta AH by delta t, the first term gives me an omega PH sin omega t and the second term gives me a minus m omega squared XH cos omega t, and therefore what I need is IH cross times that. The m cancelled out here, the m cancelled out here, so there is no m out there, and this is what I have. Yeah. So now coming back to this step, IH cross delta AH by delta t gives me an IH cross omega PH sin omega t minus IH cross m omega squared XH cos omega t. So the commutator of A with the Hamiltonian plus IH cross delta A by delta t is 0. This cancels out with that and that cancels out with this. What is the point that one is making? A does not change with time. However, that does not mean that it commutes with the Hamiltonian. I have created a problem, a situation where the commutator is not 0. There is an explicit time dependence and that makes a non-zero contribution, but between the two of them the total change dAh by dt is 0. So much for the Heisenberg picture. I have given an example, and in the subsequent lectures we will take up dynamics more intensely and look at the various ramifications of time evolution.